And this is a list of people who work with us, some students and postdocs at KTH. Then we have Drew Bamitra at Nordita, which is a Nordic Institute for Theoretical Physics in Stockholm. Professor Breghem and some co-workers in Delft in the Netherlands. Then Francesco Picano, now in Padova in Italy. And then one of the survived organizers. And we will talk about at the end a little bit. So what we want to do is, our challenge, so to speak, was to study dense suspension, both of the formable and rigid particles, in the presence of inertial effects. So we are not going to do rheology, although at the end we did something. But the idea is to take dense suspensions where the distance between the particle is of the order of particle size. So we need to account for all possible interactions. And then to have inertial effects, because we think that the suspension, when in many applications, they are really flowing in a turbulent flow. What we do, of course, my talk is mainly about large-scale numerical simulation, where we develop algorithms that we use for rigid particles initially, and then I will mention a little bit droplets and bubbles. And one thing that I want to say with this slide is that, okay, some people call these direct numerical simulations, but of course, as soon as we get into multi-phase flows, there is need to do some modeling. So is it really what, well, maybe, so we just call it larger scale numerical simulation, because just for the simple case of a rigid sphere, we need to model numerically, for example, collisions with the wall, lubrications, and so on. So what we solve, we're now talking about rigid particles, basically we solve Navier-Stokes equations in relatively simple domains, coupled with the equation for the motion of rigid particles, where we have gravitational forces and atomic forces acting on these particles, where here we have linear and angular velocities. The problem of all of this is that what Professor Prosperetti called the curse of the boundary condition, the fact that we need to impose no slip, no penetration on surfaces that move around in the flow. So how do we do this? Well, what we do was an algorithm that is becoming more and more popular and relatively efficient is this inverse boundary method. In this case, you have two meshes, one Eulerian regular mesh where you solve for the Navier-Stokes equation, and then you have with additional forces coming from this Eulerian mesh, which is used to track this rigid particle in the flow. So we have an Eulerian mesh, these black dots that define a shape, like in this case a spherical particle, but we also look at different shapes. And then we have the Eulerian mesh for the fluid, and then this Navier-Stokes equation have additional force F, which comes from the difference between the velocity at the Lagrangian point and the velocity at given by the Eulerian grid, which forces the no-slip, no-penetration boundary condition. The problem is, as I said, is that if you have this fixed Eulerian mesh, at some point, especially if you want to do inertial flows, because this actually we don't really need when we have low Reynolds number flows, rheology, limit of Stokes flow. But then, since we have inertia, there will be collisions, particle walls, for example. Then at some point, your mesh will be not adequate to resolve the viscous flow in between the two. And what we do in this case, we use a correction for the force between the two, which is based on analytical solution of the Stokes equations. And then at some point there will also be a collision. In this case we use a soft sphere collision model. So we allow a weak penetration between the two particles, which is usually not as big, it's something like 2% of the particle diameter. So, but this is good because it allows to have a little bit longer time step. So this is what I did before, large-scale simulation of particles, fully resolved particles in turbulent channel flow. This we can see that the particles organized in structures like streaks, similar to what you would expect in single-phase flows. We have animations here of the same simulation. These are the largest we did, where we have like 640,000 particles. And each particle has a size which is 6. The diameter of each particle corresponds to 6 Eulerian meshes. So and one of these simulations is about 10 million CPU hours on these modern computers. And this was used to analyze, for example, the modulation of turbulence in the presence of particles. And in particular, we have this paper here where we look at how the log layer is modified in the case of rigid particles. But then also we look at different shapes, like here we have prolate particles, and here we have oblate particles. These are all around the channels. This is just to show, to make the movie a little bit more understandable. For example, in the case of oblate particles, we see a drag reduction compared even to the single phase flow. This is because the oblate particles, they are disk-like particles. They kind of preferentially align with the wall, a little bit lifted from the wall. So they create kind of a shield between the near wall region and the bulk. And in this case, they kill a little bit this turbulent regeneration cycle, so that in this case, we have a drag which is lower than that you will have in the presence of only water. This was also interesting because the drag, instead in this case, the drag is not as reduced as in this case, because these oblate particles, they rotate around the wall normal direction, and by doing this, they increase the mixing in the near wall region. Another thing we are doing now, the movie is actually looking at elastic walls and particles. This is also, we are looking now at the results, and we see how one thing we see immediately is that because of this deformation of these elastic walls, particles are lifted away from the wall. So there is a region close to the wall which is depleted of these rigid particles. So that's, and then also, there is a relation between the drag increase due to the elastic wall and there is a relation between the drag increase and the elasticity of the wall, so the time scale of the elastic waves in the solid as well as the time scale of the turbulence.
So roughness scale is correct or on your drawing?
Sorry?
So roughness 8 is correct because it's comparable with the size of the particle?
Yeah, in this case, yes. This is it's elastic wall that deforms, and actually you can call it roughness because we show in one of these papers. It's not this actually. This is wrong. It's another paper that without particles, this elastic wall has an average fluctuations, and if you call this as a roughness, if you consider it as a roughness, you can use correlations that people use for rough walls, and you get the same prediction for the shift of the log layer and stuff like that. But what I want to talk today more about in this first part at least is heat transfer in particulate suspensions. So this is closer to industrial application, and we think this is also interesting because so we add more physics to the thing. So there are a lot of examples. We are now focused a little bit on fluidized beds, but not too much. But first, what we looked mostly at was heat transfer in pipes laden with particles, funnel-sized particles. And this was motivated by a collaboration with Tetra Pak in Sweden, and they built machines to deal with food, to process food. And what was the problem there? The main problem in this case is not really the pressure loss in these tubes. That's okay. The thing is that these particles, since they are in this food, they need to be inside. They need to have a temperature which is above a certain threshold for a certain amount of time, and need to be sure that the temperature at the center of the particle is high enough that they can consider this as, clean or not dangerous, so that it can really be sold afterwards. So that was interesting because we have a coupling with turbulence, heat transfer, and then also we need to have the heat transfer inside the solid particles. So what we do here, we couple the IBM with some kind of volume of fluid approach for the temperature, where we saw the temperature diffusion also inside the solid phase, which is here is the gray. So we have basically a phase indicator function which identifies the fluid part and the solid part, and we have a thermal diffusivity which is a weighted average between the one in the fluid and the one in the solid, so that we can have different thermal diffusivities, although when it deals with, for example, peas and carrots, like they're interested in, the thermal diffusivity is the same. It's almost one. That's not, but we change in the simulation just to have more insight. So the first thing we did, just to validate this, we consider a simple quiet flow, laminar flow with particles, different particle Reynolds numbers. And what we do here, basically, we compare all our simulation, where we change the particle Reynolds number, with the experiments by Metzger et al. Actually, they did a lot of experiments and some simulation, and they come up with a correlation, which is this continuous line, which relates the effective heat transfer in the suspension. So the relative, let's say, the ratio between the effective heat transfer and the nominal heat transfer, the nominal one in the absence of particle, they relate this to the phi, which is the volume fraction of the particles, and the Pecklin number, which is basically related to the heat diffusion. And so we see that we follow this, but of course, when the particle Reynolds number, so the inertia is relevant, then we have we depart from this theoretical prediction. At time volume fraction, as in the experiments, we see that now there is a sort of saturation. Now we'll get back to this. So now the main thing is this work about particulate pipe flow. So we will consider two Reynolds numbers, one which is 370, which is basically a laminar flow, or still it's a chaotic flow when you see it with particles. And then another one which is as turbulent as we could do, we can say, is a Reynolds 180 pipe flow. And then we have different particle sizes. This the one that actually needed comparing the experiments, they do a tetrapack. And then we see here in the case when the particles are 1/15 of the diameter or 1/5. So they're a little bit big, different volume fractions. So if we start to see what happens in laminar flows, here we see basically the effective heat transfer versus the volume fraction. This black is for the biggest particles, and this one is the smaller particles. And we see that heat transfer increases as the volume fraction, but then we have some kind of saturation. And then the larger the particle, the more efficient is the heat transfer in the laminar flow. There is more mixing. And if we look at the pressure drop across the pipe, then we see that it's kind of independent of the particle size, which what we would expect just from a rheology consideration, right? When you have a apparent viscosity suspension, usually that's independent of the particle size. So basically we see that if we can enhance heat transfer with bigger particles, but you will not pay a price in pressure drop in this particular case. Things are different than turbulent flows. So we did now simulation with, again, from 0 to 40% volume fraction. There's this Reynolds number. This is the history of the heat transfer, how the heat from the wall is transferred inside the suspensions. And we can see that the transfer is initially faster. So this Nusselt number is faster in the case of higher volume fractions. But then after a while, there is a switch, and then the heat transfer continues to be more efficient, but when you have lower volume fraction, so 5%. And why is that? Let's see if I don't have the slides. So this is what happens in the flow. This is the heat. This is a cross section. This is the temperature field. Sorry, 5% and 40%, and the particles here are not displayed. What you can see, okay, you see here is faster. 5% is initially lower, but then after a while, the temperature the flow is colder in the center, while this one becomes more uniform. And why is that? This is because particles tend to migrate towards the center of the pipe. Because they are large, they tend to migrate towards the center of the pipe. And here we have a kind of a laminar core where the heat transfer is low. It's pure diffusion. Instead, when you have only 5% volume fraction, this effect of migration is not there. So the flow is turbulent all across. And this makes the heat transfer then eventually in the long run faster. So if, let's see, oh. So this is what we see. This is basically the particle volume fraction towards the distance from the wall. So this is the wall, and this is the center of the pipe. You see that the higher volume fraction, you have a migration toward the center. So the flow is laminarized by the fact that you really are dense now in the core. And laminar flow is basically lower fluctuations and lower heat transfer. And here you can see from the fluctuations, if you take, for example, the wall normal fluctuations, you can see that in the case of 40% volume fraction, you have a peak of fluctuation close to the wall. But then these fluctuations in the wall normal direction, they go to 0 towards the core of the pipe. Instead, if I have 5% or single phase turbulence, I have less fluctuation close to the wall, a peak in the intermediate region, and then I still have some kind of isotropic turbulence in the core of the pipe. So when it comes to heat transfer, what we have seen is that we have large particle-induced significant heat transfer enhancement, but of course it will not cost too much in terms of wall drag. But when you have high volume fraction and turbulent flow, then you can have this unexpected effect or negative effect that the particle migrates towards the core, and this is an effect we see also in the channel, for example. But this reduces mixing in the core, so that it will be more difficult to have the heat transfer going towards the core. So what we are doing now is different shapes, because actually the tetrapag likes carrot cubes. And that thing is, this is the fluidized bed simulation we are doing now. So in this case, I have particles which are hot, and they are blown upwards, but they are heavy, so they tend to fall. But still, in this case, the impulse flow dominates. And then they have a thermal wake that also tends to accelerate them upwards. In this case, we have to do very long domains to be able to have inflow of cold particles, the blue one, and then as they cluster and warm up as they move upwards. Now, the other thing I have two other things, three maybe, but let's see. I want to show. This one is emulsions in shear flow. And why we do this? Because, again, maybe to stress, if you think in terms of the future discussions, how important is really these short-range interactions, how much they can change the physics. And so we can, this is done by collaboration with Sergio Caserta in Naples. We did the experiments. So this is experiments, and now is performed, but this is a published one in the Langmuir in 2012. This is an emulsion of droplets of two liquids or kind of two different oils. And this is what happens after a long time. We see that these droplets segregate, so we have span-wise bands. So in these emulsions, if you just shear the emulsions and we wait long enough, I don't know what this now, I can't read from here. But for these long shear times, like 6,000, let's say already at 3,000, you can see something. You see this segregation, and you have span-wise bands. And how do we explain that? Well, one explanation to put forward is that, well, if you look at the rheology, so the effective viscosity towards the volume fraction, you see that if the viscosity ratio between the carrier fluid and the suspended fluid is order 1, you have a increasing viscosity with the volume fraction. But in the other case, when the fluid inside the droplets is less viscous, we can have this different concavity. So now, what means that if you are here, if you have 30%, if you are in this situation, if you have 30% volume fraction, whatever, now I'm confusing. Okay, so that for the system will be more efficient. So if you take this curve here, the total viscosity will be less if you segregate, because if you have, let's say, 15% volume fraction, okay, this is the total viscosity in the fluid. But if the system will segregate between 0 and 30%, then the viscosity will be the average between the two, so it will be less. So the system will tend to be to have lower dissipation by forming these bands. So what we did with the simulations of these some emulsions in shear flows, and here we use a method we basically copied from Japan, we can say. It is M-thing. This is multi-dimensional tangent of a parabola for interface capturing. This is quite efficient because it's a volume of fluid method. And in this case, the numerical fluxes can be evaluated by integrating this hyperbolic tangent. So you assume the interface to have this hyperbolic tangent. And then you approximate normal curvature in a classical way, but you still assume that you know exactly these hyperbolic tangent functions. You don't need to do geometric reconstruction, which is usually the most time-consuming part in this volume of fluids. You can have easily linear, quadratic, wire approximations. And this is shown to be very efficient, fast, because it's extremely local, if you have parallel computation, and you remove this spurious current. So this is good. So this is what we saw. If you look at the viscosity of the suspensions, then we see again that if you have fixed capillary number 0,1 closer to the experiments, we see that when the viscosity ratio is 1, we get more or less this increase. When the viscosity ratio is 0.01, then we have this different concavity. So the viscosity tends to decrease at higher volume fraction. This is now effective viscosity for different capillary numbers. So we increase in the capillary number, we move to red to green. So we see that we have some shear thinning when we increase the deformability. So if the droplets deform more, the viscosity decreases. And this is the points from the experiments, which are relatively close. Oops, that's what I want to say. But then the thing is that what I want to mention before, what is really important in these emulsions is really the presence of surfactants and what happens when there is where there are short-range interactions. So what we wanted to look at just a simple thing, the simplest thing we could do, one parameter model, where we have basically a repulsive force between two droplets when they come close to each other. So this is a repulsive force which depends on the distance of the two interfaces, some model coefficient that we tuned, and then the relative velocity and the size of these droplets. So we apply this force so that there is basically no merging in the volume of fluid. Very simple things, can be done in more sophisticated ways. And so what we see here is that when we have effective viscosity imposing some kind of collision or repulsion, we have this behavior of the viscosity versus volume fraction, which is similar to the, this is the RS feed, this is the form of rigid particles we started before, and this is basically now these emulsions. We have a behavior with an increase, which is similar to the one you see for suspension of rigid particles. As soon as you remove collisions, you behave a little bit like, as soon as you remove coalescence, you behave a little bit like rigid particles. So it's the opposite behavior. And in fact, now what we are doing now, we start to relate this different rheology, the fact that you move from an upward bending viscosity curve to one which moves down, to the formation of bands. And we see that if we start with emulsions, we allow merging. If we start with bands, the concentration of volume of fluid, the concentration of this second liquid remains aligned. So you keep these bands, and they are stable for very long times. Now the simulation is a longer shear times, and we did different cases. Also, this other case, we still have stable bands. But as soon as we put repulsive forces, so we make basically the merging more difficult. It still may happen if they bond to each other with a certain strength. So, but if we make it more difficult, then we see slowly some kind of diffusion. Now this is a little bit too short time to see. It is a extremely slow process, but we have now we have seen this. You see in the movie we can start to see a little bit of opening. So now the last thing I want to mention now is there's a recent work we did this summer in Stanford, in the research program, where we look now of homogeneous shear turbulence with finest size bubble and droplets. Is this running? No. Okay. That's why this was a movie. You see droplets and bubbles in homogeneous shear turbulence. Now it's moving, but let's go. It's too heavy, the simulation. So this is basically a simple uniform shear flow with 3 periodic boundary condition. And we use this because this is a little bit more complicated than simple homogeneous isotropic turbulence, but also because you can get to a steady state homogeneous shear turbulence where we have a good balance between production and dissipation, and where you, which according to Jimenez and where you reproduce in an artificial way this log region in a turbulent flow. In fact, if you look at what we do, we study the interaction between droplets and turbulence, and so far this has been done in simulation only for the case of decay homogeneous turbulence, decaying isotropic homogeneous turbulence. But then, since it's decay, it's really short time, so we don't really get to some kind of steady state. So here we want to look at this visualization. So what we look at this, but we have 2 slides. One is about the dynamics of the dispersed phase. What happens? One of the big questions in this case is, will you get to some kind of steady state distribution? And if you look at this plot, this is the number of droplets versus time. And we see that for almost all the cases, especially for the Weber number, so surface tension is relatively strong, we get to more or less a steady state, a statistical steady state. And this number of droplets now grows proportional to this Weber number, where now here we define the Weber number with the density. In this case, the density ratio is 1, the fluctuation in the flow plus the shear that we impose, where lambda is the integral time scale of turbulence. So if you use this Weber number, we actually manage to more or less collapse all this number of droplets and number of droplets in the flow along a line. And note that actually in the real simulation, we vary the surface tension by like 2 orders of magnitudes. But then if we can collapse the data in this way, then we see a relatively good collapse. And now what we did now, we compare here with the theory by Ince, about which relates the largest, basically the largest size of droplets possible in the flow to the turbulent dissipation. So droplets will not be larger than a certain size, because above that size, basically they will be immediately disrupted by turbulence. So what we did, we counted the number of droplets. So basically, this is the volume versus this is the diameter of droplets normalized by the largest one, and this is the volume occupied by droplets with size lower than this d. So that means that if I take this line, which is 0.95, it means that 95% of the volume of the suspended phase is in particles which are size below this d. So if I take this blue line, it means that 95% of droplets will have a size below this. Now, this is exactly what Ince did, actually. So if we put our data in against this prediction, we get this quite good collapse, which is actually, I think, better than the one he himself shows in his paper. But I don't know, we have to look at this case, but it's relatively good. So there are things, and now, okay, this is the droplets, they get a steady state, which actually I would say is the first time we get in this kind of simulation. Then we look at turbulence modulation, what happens to turbulence flow. We have an increase of the turbulence dissipation and also of production as we decrease the Weber number. So as the droplets become less deformable, a little bit like before. If they are rigid, they will affect more the flow, so we have an increase of dissipation. And then we have a decrease of the Reynolds number, or the Reynolds lambda in the flow, with the Weber number. It means the flow becomes more, the structure becomes larger in practice. The smallest eddy becomes larger because the fluctuations in the flow actually will not change too much. So this decrease in Reynolds number is really related to the variation of the size of the vortices. And then the last thing we observe is quite interesting is that if you look at production density, so is the production in each volume divided by the total production, we see that it's higher in the carrier phase, green, than the droplets. It means that you create production in the carrier phase, not inside the droplets. In percentage, right? There's a density. But also, if you look at the dissipation, we see that dissipation density is about 50% larger inside the droplets. It means that the turbulence, the viscous dissipation, proportionally is much stronger inside the droplets than outside in the flow. Which, but we haven't done it yet. We want to look at the topology of the flow inside the droplets, and I would expect not to be pure rotation. Otherwise, we don't have this relatively strong dissipation. So this is a summary of this. The number of droplets and surface area related to this droplet grows with the Westermann number. They both grow. The Ince scale seems to work also in the presence of shear and coalescence, because Ince did this analysis for homogeneous droplet turbulence, and he assumed pure only breakup. So he didn't consider any coalescence kernel or something like that in the process. Okay, turbulence attenuation is more evident if the droplets are more rigid. And another thing that we see here is that now, if we start to change the density and viscosity ratio, we see that it changes completely. So all this, what we've done, I discussed so far, is basically density ratio 1, so it's like oil in water. But if you take this case, where the carrier fluid is heavier, so this is like air bubbles, then already visually we see very different behavior. So this is what we want to investigate. Now, this is the last thing I want to mention, because it's done together with Sarah. So no, but this is quite interesting. I think I like it a lot. So we started to do simulation of turbulence flow over elastoviscoplastic fluids. So we have fluids where you have elastic effects and at the same time a yield stress. So if you are below a certain tau 0, the fluid behaves basically as an elastic solid. If you are above this tau 0, you yield the fluid and then you retrieve this basic Oldroyd B model. You can change to FNP, but in this case it's Oldroyd B. But so we did something about porous media, but I just want to talk about turbulent flow, and this is now very accepted. We look basically at turbulent flow of these elastoviscoplastic fluids. Let's see, it should run. Yes. And in this case, we see this is a side view of the flow in the channel, a simple two-dimensional channel. We see the formation of these dark regions, brown region, which are basically where the fluid is yielded. So this is like gel-like solid regions that form and destroy during the flow. And this we see close to the wall, this near wall structure and some ejection events. Here we see from a cross-section a similar behavior. And all the simulation, the simulation we presented here are all done with very, very low elasticity. So we don't really have elastic effect yet, but we are studying now. So this is what happens. This is the classical Reynolds tau 180 that Kimon and Moser did like 87. So increase the Bingham number, we see that we have the increase of the solid region in the center until you have complete laminar flow when this plug flow becomes too large. And then we can see also this, the formation of these structures which modulates the turbulence, and we have overall actually a drag decrease. Okay. Thank you.